All right, here in number 25. 25 here is a half-life type kinetics, talking about kinetics in terms of half-lives. And for this, the thing to get is, this is what happens. So the half-life is the time for the concentration to drop by a half. So if it starts at 100%, it over whatever the half-life is drops to 50, and then the 50 drops to 50% of 50. So half of half, that gives me a quarter or 25%. And then if this kept going, 12.5%, and then finally 6.25%, and on and on and on. Never technically getting completely to zero, getting lower and lower and lower as it goes over. And then this problem tells us that this half-life in this particular case is 14.2 days. And it asks us how long will it take to get to 20% of the initial activity. And since this is going to be a multiple choice question that you will see, so it asks us 20%. So 20% is right in here somewhere, pretty close to 25, closer to 25 than to 12.5. And so it took, to get to 25, it took 28.4 days. And then just to make sure that we haven't went past the other number, let's see, 32, 42, 42.6, I think. Yeah, 42.6 would be here. And then if we look at our options, we see that, well, to me, the one that looks the best is, so around 43 days is 12.5%. So that we've overshot. We went past 20. And so it's not B, it's not C, it's not D. And it makes a lot of sense to me that to get to 20%, 33 is just a nudge past 28.4. And so the correct answer here is A, 33.0 days. We'll continue on with that theme for this next one. In this one, it is cyclobutane to ethylene, so C4H8 gas. So this is 4 carbons breaking down into 2 carbon species. Okay, this is that reaction happening. And again, we're given a half-life for this particular reaction. So our T1/2 is equal to, and I'm going to just go ahead and call that 23 seconds, because we're going to estimate just like we did with the previous problem. And 100%, and then in 23 seconds that would be at 50%, and then another 23 seconds that would be at 25, and 12.5, and 6.25, 23, 23. Okay, and it asks us how long does it take to get down to 10%. So then we're going to be somewhere in here, okay, just a little bit past this, closer to 12.5 than to 6.25. So to get here, this is, I think I can do this one in my head, 20, 40, 69 seconds to get to right here. Okay, 69 seconds. And then just to make sure we don't overshoot, how long would it how long would it take to go there? This, to go all the way from here to here, is 92 seconds. And so, what looks good? 69, yeah, 75.5. 75.5 seconds. Okay, it needs to be a little bit longer because we were still at 12.5 at 69 seconds. So definitely not as long as 52.5233 seconds. And so looks like a good answer to me. Okay, here rate, and we're given the rate equals some constant K, and it says A is to the first order, and B is to the second order. And so let's say then, let's call this, it's not going to be super exciting, rate 1 is going to be K times basically just what I've written. Okay, and then rate 2 is going to be K times, and it says if we cut the concentration of A in half, so 1/2 A, and then we double the concentration of B. Okay, and then this is where the magic happens. We double the concentration of B, and so for this rate 2, it's equal to, I'm going to put all these factors out here in the front, 1/2, and then 2 squared is 4, and then K, and then A, and then B squared. So this is going to give me 2. 1/2 of 4 gives me 2, and so this rate is going to double if I cut A in half but double B, because B has a much larger effect because the concentration of B gets squared. This is 128 here is one where really you only need to know the equation to be able to make sense of this. So for 28, the osmotic pressure is equal to the molarity times the gas constant R times the absolute temperature. And it asks which information we would need to know in order to determine the molar mass. And so we would need to know, we would need to know the temperature, and we would need to know the mass of the solute and the volume of the solution. And I said this wrong when I was doing this in the lecture face-to-face. So we need all 3 pieces of information. We need the temperature, the mass of the solute, and the volume of the solution to figure that out. All right, number 29. This is a real common type of problem to see from Gen Chem 2, which is a change of one concentration to another. So they've given you 3.539 molar HNO3, and they've asked you to convert that into a molal concentration. So the big M, capital M, is moles of solute, in this case HNO3, per liter of solution, versus little m, which is molality, okay, and notice the difference here. Moles of solute on the top for both, liters of solution. Solution is composed of both the solute and the solvent, in this case water. The solvent is just the solvent. And so we have to do some work to sort all this out. We absolutely have to have, and this problem provides us with a density. And this density, I want to be very specific with these units, 1.150 grams of solution per 1 milliliter of solution. Okay, this is not the density of the solvent or something like that. This is the density of this solution. And so what's nice about that is we've got liters of solution. We can turn that into a mass of the solution. Okay, so I know that, so 1 liter of solution, and don't let this blow your mind, but a gram per milliliter is the same as a kilogram per liter. It's just the same as taking the top and bottom here and multiplying by 1,000 to do that conversion. So 1.150 kilograms of solution over 1 liter of solution. Okay, so now we know the mass of the solution. And remember those solutions still, it's two components, the solute and the solvent. So we need to figure out how much solute is in there so we can subtract it out. And so we've got 3.539 moles of HNO3. They've kindly given us the molar mass. 1 mole HNO3 is 63.02 grams. Okay, 223 grams of HNO3. Let's go ahead and, since we got everything else, and write this in kilograms. Now we can just do a direct subtraction here. So 1.150 minus 0.223. Okay, so 0.927. So this top one was solution, and this was the solute. And so if I subtract the solute from the solution, I know now the solvent. Kilograms. All right, almost there. Oh, a lot of work. Molarity then is 3.539 moles of HNO3 per 0.927 kilograms of water, because it's an aqueous solution. Okay, 3.82 molal, little m. Okay, another one of these concentration to concentration calculations. Again, pretty common on these types of exams. So we're given that a sports drink solution is 4.50% sodium chloride by mass. And I can take and translate that, 4.50 grams of sodium chloride over 4.50 grams of sodium chloride plus 100 minus 4.5, 95.5 grams of water. Okay, so I think we got a pretty short path here. We want to go to molality, which again is moles of solute per 1 kilogram of solvent. Well, that's nice. We know the mass of the solvent. I'll go ahead and make that into kilograms, 0.0955 kilograms of water or solvent. And so now we've got to figure out how many moles of sodium chloride is in there, and that should be easy peasy. Since we were given the molar mass. Okay, 0.0770 moles of NaCl, almost there. Molality, 0.0770 moles of NaCl, 0.0955 kilograms of water. 0.806 molality.